Let me first record. Okay. Can you hear me now? Okay. So I will continue the introduction, the first chapter. Okay. Any question from previous parts from the previous session? Any question? Okay. So we continue with the introduction and vibrations. Vibrations will cause some physical phenomena. For example, we will have spectacular mechanical failures, or sometimes when we have fatigue, we will have more rapid wear of machine parts such as bearing and gears. You studied this type of phenomena in MM312, I think, in this type of courses. Or sometimes the vibration will cause loosened fasteners such as nuts. But the important phenomena which is studied here in this course is resonance, and the resonance will happen when the frequency of the external force is equal to the natural frequency of your system. In this type of excitation, you can see that the amplitude of the displacement or the amplitude of the response start to increase, and it will increase without any bound, and finally it will cause to the failure of your system or your mechanism. Okay, your system can be a building, as I told you, or a bridge, or any type of mechanical system. So in this course we mostly focus on resonance, which is in fact due to the, again, natural frequency, and you will see again the natural frequency will play an important role in this course. Okay, for example, here we can consider three damped 1 degree of freedom systems. Here, all of the systems have the same characteristics. I mean, the mass, the stiffness of the spring, and the dimensions, everything is the same. But these three systems are subjected to three different forces. The purple one is subjected to a force with frequency 0.4. Yeah. The blue one is subjected to a system with the frequency 1.01, and the red one is subjected to an external force with the frequency 1.6. The natural frequency of this system is 1 Hertz. Here you can see, despite the amplitude of the external force is a constant value and it's equal to F naught, but the amplitude of the response for these three systems is different, and also the frequency of the response is different. Of course, here, because these three systems have damping, here you can see this is a damped 1 degree of freedom system. So due to the damping, we don't have resonance, because the damping will cause that there is no resonance in these systems. But in the blue one, which the frequency of the excitation is close to the frequency of the system, 1 Hertz, you can see that the amplitude of the response is more than the two other responses. So you can see that the frequency of the excitation or the frequency of the external force will affect on your response amplitude and your response frequency. And in this course, we will study this type of phenomena completely, okay? So the basic concepts of vibration, first we need to introduce the elementary parts of vibrating system. In any type of vibrating system, we will have a part for storing potential energy. In this course, this part is usually a spring, or in the continuous system, it will be the elasticity of your structure. For example, if you have a beam, the elasticity in your beam or in your structure is considered as a spring, or generally it is considered as a part which stores the potential energy. The second important part is, or the second important element in your vibrating system is a part for storing kinetic energy. And again, in this course, we will have mass, but in continuous system, we will have the inertia. Again, if we refer to that beam, the inertia or the mass moment of inertia for that beam will play this role. And the inertia will store the kinetic energy. If you remember from dynamics, when you extract the kinetic energy for a particle, it was equal to the half mass times by velocity squared. And the kinetic energy for a rigid body, it was equal to the mass moment of inertia in a substitute by the mass, and it was equal to half times by the mass moment of inertia times by the angular velocity squared. So this is the kinetic energy, potential energy, and finally we will have a part which causes to the lasting, which causes to last the energy. And in this course, we call it damper. We will have different types of damping, and you will see, I think in the next chapter, we will investigate different dampers. But generally, there is a part which cause to lose the energy in your system. So finally, we can consider a vibrating system which involves the conversion of the potential energy into the kinetic energy, and again from kinetic energy into the potential energy. And this is a continuous cycle. And during these cycles, we will have some loss of energy due to the damping. And finally, by decreasing the amplitude of the response, the vibrating will vanish. So this is the whole cycle of your system. Here again, the black one, the black system, this one is an ideal system without damping. And you can see the amplitude of the response will remain the same. But the blue one has damping. Both of them start with the same initial condition. Here at point 2, you can see both of them have the same initial amplitude, but over the time, the amplitude of the blue one, which has damper, is decreasing, and after a while, it will be about 0. So this is the effect of the damping here. And usually in all of the systems in the real world, we have damping. But in this course, first we start with the systems without damping to extract the response and the solution for this type of systems. And then we will study the effect of damping on a system. Any questions so far? No questions? Okay. So one of the most important concepts in this course, as you studied in dynamics, is the number of degree of freedom or degree of freedom for your system. You know that the degree of freedom, in fact, has a general definition. It's a minimum number of independent coordinates that we require to determine the complete position of all parts in your system. So this is a general definition, and according to this definition, we can obtain the DOF of your system. In vibration, we have a general rule that according to the number of DOF in your system, we will have natural frequencies. For example, in a system with 1 degree of freedom, which we call it SDOF or single degree of freedom, we only have 1 natural frequency. But in a system with 2 degree of freedoms, we will have 2 natural frequencies, and so on. I mean, for example, in a continuous system with infinite degree of freedom, we will have infinite natural frequencies. I mean, in a continuous system such as a beam or a plate or shell or any other continuous structure, we will have infinite natural frequency. But always the most important one is the lowest one, or the first natural frequency, which sometimes we call it the fundamental natural frequency. Okay. Here we have some examples. Here we have a pendulum. How many degree of freedom here in this system we will have? Or what's the degree of freedom for this system? We have X. If we want to obtain the position of mass M, we can use X or theta. What is the degree of freedom for this system? Can you tell me? Exactly, because you can define X in terms of theta, because in at each moment you can write that X is equal to L times by sine theta. So X is not an independent parameter, and it's equal to L times by sine theta. Yes. So here you can see that X is not independent, and the degree of freedom for this system is 1. But what about this one, this system? Again, we have X and theta. What is the degree of freedom for this system? Y2. Here we have X and theta. Again, we can define X as a function of theta, yes? Because this length is a constant value. So again, you can define that X is equal to, if we call it, for example, R, we can write that X is equal to, again, R sine theta. So when R is a known parameter, we can define the X as a function of theta. So again, X is not an independent parameter. Clear? So again, the degree of freedom here in this system is 1. So the position for this particle can be obtained using the R and theta. And this one, It's clearly a system with 1 degree of freedom. And in this course, we mostly deal with this type of systems. You can see a mass M, a stiffness K, a simple spring mass system with 1 degree of freedom. What about this one? We have x1, x2, and x3, y1, y2, and y3, or theta 1, theta 2, and theta 3. What's the degree of freedom for this system? Yes, this is 3 exactly. Thank you. Because again, you can write x1, x2, and x3 as a function of theta 1, theta 2, and theta 3. And for y1, y2, and y sub 3, again, we can write the same relation. x1 is equal to L1 sine theta 1, and y1 is equal to L1 times by cosine theta 1. So you can see in this system, again, we have 3 independent parameters, theta 1, theta 2, and theta 3. Of course, if you want to extract the equation of motion for this system, you can write the equation of motion in terms of x1, x2, or x3, or you can use y1, y2, and y3, and also theta 1 to theta 3. So you can use a combination of these parameters, but you should know that the degree of freedom for this system is 3. And remember that there is one natural frequency per degree of freedom. Here we have a system with 3 degree of freedom, so there will be 3 natural frequencies for this system. And also there are 3 equations of motions. So there is 1 natural frequency and 1 equation of motion per degree of freedom. And here we will have the equation of motion for this system is a system of 3 coupled equations with 3 natural frequencies, and you will see later with 3 mode shapes in the last chapter. And what about this system? What's the degree of freedom for this system? Here we have a slider which is connected to a pendulum. Here we have x, and of course this is the lowercase x, and we have uppercase x, this term, and also we have theta. Thank you for your answer. Oh, sorry. Let me use this notation. So we have uppercase x, lowercase x, and theta, and also we have y. This x, the lowercase x, is equal to L times by sine theta. So this x is not an independent parameter. This y is equal to L times by cosine theta. So it's not independent, and it's equal to a function of theta. And finally, the uppercase x, which is an independent parameter because it's not related to theta, and theta is another independent parameter. So the degree of freedom for this system is 2. So here we have a 2 degree of freedom, and this one is 3 degree of freedom systems. Clear? Any question? No questions? Okay. As I told you, we will have two different categories in the materials or in the systems, and that's the discrete or continuous system. A discrete or lumped parameter system, in fact, is a system with finite number of degrees of freedom, similar to the system that we studied in previous slides. And a continuous system or a distributed system is a system with infinite number of degrees of freedom. So in the real world, in fact, there is no discrete system, and this approximation is the approximation that we used in the rigid bodies for dynamics. If you remember, we don't have any rigid bodies, in fact, but in the real world, we assume that some structures or some bodies are rigid and we can neglect their deformation. Here in vibration, there is no continuous system, in fact, but we can assume that they are similar to a system with finite number of degree of freedom. For example, we can assume a distributed beam as several lumped mass and several springs. So we can model this type of systems, the continuous systems, as a discrete system, and we can find the fundamental natural frequencies for these type of systems. And you will see, for example, if you find the natural frequency for a continuous system by assuming the equation of motion, you will see, for example, if the natural frequency is x, and if you approximated this system with a discrete system, you can extract the fundamental natural frequency, which is with an acceptable error is equal to x. So we can model this type of systems as a discrete system. And in this course, we only concentrate on the discrete systems. I mean, we assume that we model the continuous system in advance as a discrete system. And now we only deal with the discrete systems and we want to obtain the equation of motion and the natural frequencies. First, we start with the single degree of freedoms and we continue with 2, 3, and multi-degree of freedoms. Okay. In vibration, we will have different classifications. The first and maybe the most important one is the free and forced vibration. Free vibration means that there is no external force. And later at the end of this chapter, you will see that in terms of the mathematics, the governing equation is homogeneous for a free vibration problem. Forced vibrations, when there is external force and the system is subjected to an external force. And again, at the end of this chapter, you will see that the governing equations for this type of problems will be a non-homogeneous equations. The second category is undamped and damped vibration, as I show you in previous slides. The undamped system, when there is no energy loss, and damped system when we have a damper which cause to lost the energy. And the last one is the linear or non-linear vibrations. Linear when there is no non-linear component. I mean, for example, the S-spring behavior is linear, and non-linear when there is some components behave non-linearly. Okay, so you know that we have linear and non-linear springs. In the linear springs, the relation between the force and elongation or reduction is F is equal to K times by X. And this is a linear relation between the force and displacement. In nonlinear springs, the relation between the force and the displacement is nonlinear. For example, F is equal to Kx squared. This is a nonlinear relation, so we call it a nonlinear component, and it causes a nonlinear vibration. And of course, sometimes due to the large displacement, we will have nonlinear vibrations as well. You will see later in, for example, in a pendulum problem, you will see by assuming a small displacement, we can convert the nonlinear equations and nonlinear vibration into the linear vibration. So again, the linear vibration is an approximation that we use in mechanical engineering to convert the nonlinear equations into the linear equations and to find an approximate solution for your system. So here we will have three different categories. The first one we will consider in this course, we will consider free and forced vibration, the both of them. We will consider the damped and undamped, both of them again. But in the last one, we only consider the linear vibration. So in this course, there is no nonlinear vibration, and we only deal with systems with linear components and a small deformation. As I told you, we can define a linear spring by this equation. F is equal to Kx, which K is the stiffness of the spring, F is the applied force, and X is the elongation or reduction in length. Also, we can obtain the strain or potential energy in a spring. This is the energy which is stored in a spring with stiffness K and elongation or reduction in the length X. So anytime when your spring is compressed or is, for example, pressured or pulled by X, the energy stored in this spring with the stiffness K is equal to half K X squared. So these are the characteristics for a linear spring. As I told you, we only deal with this type of springs and we don't have anything to do with nonlinear ones. And again, just to remind you that in the real world, there is no linear springs, but this is again another approximation. But this approximation is very useful and it's usually it's acceptable because most of the time we can assume that our spring is linear and it has a linear behavior. Okay, for today, my time is almost finished because I have less than 2 minutes. So I will wrap up if you don't have any question this session. And tomorrow we will have another link for Zoom meetings. And I will upload this on Moodle and you can use this link for the tomorrow sessions. Any question from this part? Okay. Okay, thank you for your attention and again, see you on tomorrow. Thank you.